for staying here for this last talk of the day. So yeah, I'm going to talk about the work I've been doing with two colleagues, Vianney Perchet, who's at the NSAE, and Philippe Rigolet, who's at MIT. So this is not actually Philippe Rigolet, it's a doppelganger, but he was too shy to let me put a picture of him here. So this is the closest picture I found of him. So the Blotto game is a game that was invented a while ago, and is a pretty famous game in the game theory. I don't know much about game theory, so I'm going to share what I know. The father of game theory is often considered to be John von Neumann for his work on this paper in 1928, where he introduced some concept and most importantly introduced the min-max theorem that is at the base of game theory, of many concepts of game theory, and a couple of, I think, years or maybe decades later, Maurice Fréchet disputed a bit the fact that he was father of game theory and attributed instead of Émile Borel, because in a paper 7 years earlier, he introduced already some concept of the game, of game theory, and he in particular introduced a game that is the Blotto games that I'm going to talk about, that has been in some way open since then. And von Neumann replied to this question, to this idea from Maurice Fréchet that he wouldn't be the father of game theory, and said that Borel did hardly initiate the theory because he did his work without reading his papers. And had he read his papers, he would probably have given up doing anything about it because the results were discouraging. So I found it an interesting piece of history. And so this game that Émile Borel introduced in this first paper is a very simple game. So here he explains this with mathematics, but it's also presented as a war game. So I'm going to introduce it with a war analogy. So you have two generals or colonels that are fighting over a bunch of battlefields, and they're given a bunch of troops. So we're going to call TA and TB the number of troops, but let's assume that it's real number, and you can divide your troops as much as you want into whatever. And the goal is you're going to split all your troops into each battlefield, and for each battlefield, the one that has the most troops just earn the place, own the place, and this is how you know which battlefield comes to whom. And to each battlefield, there will be assigned a value that will be different for a player B and the player A. So for a certain player, one battlefield might be worth more than for the other one. We'll call this value VBI for the value of the battlefield I for the player B, and VAI similarly. And then the goal of the game is to maximize your utility, and the utility is the sum of all the values of the battlefields that you won. So it's a two-player game that I will call A and B. Without loss of generality, I will suppose that the budget, or like the number of troops of the player A is greater than the one of player B, or equal. And so, as I said, among those n battlefields that we're going to play, we will have different values for A and B. So I will denote VA1 or VAI for the values attributed for player A, and VBI for the one for player B. Without loss of generality, I will assume that the sum of all these values is equal to 1. Otherwise, my game is just the same with a different scale factor. And there are different kind of variants that have been considered. One that is an all particular case of this one. One is budget can be supposed symmetric, so that the budget of both players or the number of troops of both players is the same. You could have symmetric values, so both players value each territory the same way. And then you could have also homogeneous values, which means that for all players, all the territories have the same value, which would be 1 over n, because I assume that the sum is equal to 1. So this is a partial literature. It has attracted a lot of people, and all these people have worked on finding Nash equilibrium. So I don't know how many of you are familiar with this concept. I will assume that maybe not all, but basically you arrive, so each player will will decide on a strategy, and a strategy is a way to assign your troops among the battlefields. And this strategy will, this couple of 2 strategies will be called a Nash equilibrium if either one, if one of the player changes strategy is going to be going to have less utility or less expected utility. So it's optimal if from this equilibrium, if one changing, it gets worse for this player. Okay, so it's a sort of optimality. And this is what you look at, or what you look for in such games. You look for a Nash equilibrium, and then hope it's an optimal strategy. All this work have been focusing a lot on symmetric values, so where the value for each player is the same. And in that case, you have what we call a zero-game sum, or constant sum game, in the sense that the sum of the utility of the player A and the player B, no matter what the strategy is always the same. So whatever one player earns, the other one will lose it. But when you lose this idea of symmetric values, you lose this idea of constant game, constant sum game, or like zero game solution. Because, well, if they were not fighting against each other, they could just say, oh, the one that you care the most about, I'm going to give them to you, and the one I care the most about, I'm going to take them. Then you would maximize the sum of the 2 utilities. And that makes the game very different. And but it's not the only reason why it's difficult, but it's one of the reasons. I'm going to look at what is the reason this game is particularly difficult. So the goal is to, like the point of the game is to distribute, to assign your troops among these different battlefields. So I'm going to call XIA the number of troops that the player A is sending on the battlefield I. And so the sum of all the troops that I send has to be upper bounded by TA. And for pretty obvious reason, whenever I look at optimal strategies, like Nash equilibrium, I have this budget constraint that is saturated. And so I have equality. And this means that whenever I play, I must have this strict condition that almost surely these 2 quantities are equal. And this is more like optimal transport, or not really optimal transport, but like optimal coupling will kick in. I here have my random variables xai, so that I'm going to need to couple in a way so that the sum is always my budget. So there is a way to deal with this problem by relaxing this condition, and instead of having a Blotto game, we introduce what is the Lotto game, and instead of having this equality almost surely, I'm going to have this equality just in expectation. So basically this amounts to say that I'm going to give, the game is going to be, I'm going to give you the marginal distributions of all my xi's, such that in expectation my constraint is satisfied, but I'm not going to tell you how to couple them. So I'm relaxing my game, and it's an easier game because my constraint is easier. And in this question, there are people that have computed the Nash equilibrium. So you may not see it. Kovnek and Robertson last year computed the Nash equilibrium in this Lotto game. And then the point of the game will be, or the point of our work was to try to find a way to be sure that you can mix them together so that the constraint of the sum being equal to the budget is satisfied. So what does this Nash equilibrium look like? So I'm taking my values assigned for each player, VAI and VBI, for each I, and I'm going to look at all the battlefields such that this ratio is bigger than the parameter gamma that I will specify later. So let's assume, in my first example, I had 3 battlefields. Let's assume that these 3 battlefields are such that the last 2 ones belong to this set. So like the player A significantly attributes significantly more values to this battlefields than B does. In that case, the solution of the Lotto games is this distribution that is either uniform or a mixture between a uniform and a Dirac mass in 0. So it looks a bit complicated like this, but basically what it's saying is that if I'm in this set where I value more these battlefields than my opponent significantly, then I'm going to play a uniform distribution onto some interval. And otherwise, I'm going to play either 0 or either another uniform distribution. And if you look a bit closely at this solution, there is another parameter, lambda, that comes in this bounds of my distribution. And that lambda and gamma becomes 2 parameters of my solution that will be fixed by the constrained budget. So it will give me a set of equations that happens to be like a bunch of polynomial equations of degree 3. And I can solve them sometimes explicitly, and when the game is in pure generality, I will approximate the solution. So the cases where we're able to find these actual values of lambda and gammas are the cases that I mentioned above. I mentioned before. Assume that we have symmetric values. So again, this means that the 2 players value the battlefields the same way. In that case, gamma is just the ratio of the 2 budgets. And in my example, or in the way I chose my budgets, this ratio is less than 1. And then lambda is going to be this other value. And then, in that case, the set of the battlefields to which I will play these mixtures is reduced to 0 for one and everything for the other one. So one player will, like the player with the less budget will play uniforms everywhere, and the other, with the less budget will play mixtures, and the other one will play uniform everywhere. So this is what has been done in previous works that I'm just explaining here. And when when the budget is the same for both players, and gamma equal 1, and then both players play uniformly everywhere. Okay, so this is saying that if they both have the same budget, all the values of the battlefields are the same and are 1 over n for all battlefields and for both players, then the best thing to do is just to pick uniformly all your random variables. Okay. This is what I just said right now. Okay, in the case of symmetric budget, homogeneous values. So now there is no coupling. That's the point, because I'm looking just at the Lotto game. I just have a constraint in expectation. So there is no coupling. Yeah, it's a pretty abstract game where instead of playing, I'm just giving the distribution that I would play if I were able to mix my thing as I want. And so the point here was to go from this Lotto solution to a Blotto solution. It's pretty clear when you just take a minute to think about it that if you have a Lotto Nash equilibrium and you are able to mix the random variables, then you get a Blotto Nash equilibrium. So we go from Lotto to Blotto by ensuring that we are able to couple these random variables so that the sum is equal to the expectation. And the sum being equal to the expectation is the same thing as asking the variance to be equal to 0. And this is known as joint mixability. It's something that has been studied independently, and that we're going to just look a little bit at for a minute. Let's assume that I have 3 random variables, and that are all Bernoullis with parameters 1/2. Then the expectation is of the sum of the 3 is 3/2. And whenever I sum 3 random variables that belong to 0 and 1, then the sum has to be 0, 1, 2, or 3. There is no other way, so I could never be exactly my expectation. So I know that all random variables won't be mixable. So here we see that it's coming from the fact that I'm adding Dirac masses, but in my case, in the case that we mentioned, there are Dirac masses, so I have to be sure that I'm not in this situation. There is a nicer case, which is a uniform distribution. So now I have 3 uniform distribution between 0, -1 and 1. So their expectation is 0, the sum of the expectation is 0, and I want to mix them. So there is here several ways to actually do that, and one way is actually you can construct it. You're going to first draw your x1 according to some uniform between -1 and 1. Then you're going to write x2 as a function of x1. So I draw the function here. I drew the function here, and I wrote it the exact value. And then x3 is going to be also a function of this x1. And when you do that, you look at the sum. You just add the 3 definitions, the 3 values of x1, x2, and x3. And then you get this thing that cancels out, and then all this equals to 0. So it's not really obvious to do that arbitrarily for any situation. And this is really for 3 random variables. So you can predict that whenever you want to mix random variables, like have joint mixability for random variables that have more complex distribution, it's going to be difficult. And also that it depends on n, the number of random variables you want to mix. Another example is the following. If I want to mix random variables that have different distributions, that are all Gaussians on the real line with different variances, then having the sum equal to 0 is the same as having the variance equal to 0. And this can be translated into a matrix property. Basically, that 1 is in the kernel, like the vectors of all 1s is in the kernel of the matrix variance matrix. And this, if you want to make an algorithm out of it, you can look at it as an SDP. You want to find a positive, semi-definite positive matrix sigma, such that the diagonal is prescribed because you want your given variances for each of the xi's. And then you want your property that the variance of the sum is equal to 0. So you have this kind of algorithm that you can use in the case of Gaussians. But our case is not a case of Gaussian. So we're going to need to do something different. In that case of Gaussian measures, it can actually be seen that there is a way to ensure that this has a solution. There is an if and only if. So my problem here of mixing or jointly mixing my Gaussians is possible, has a solution if and only if the higher standard deviation is less than 1/2 of the sum of the others, or of the sum of all of them, sorry. Said in another way, it's the same as asking that the highest, or the largest, sorry, standard deviation is less than the sum of the others, which is asking, if we think of it as the values in my battlefields, is asking that there is not one battlefield that has much more, that has more values than all of the other combined. So getting a bit closer to our situation, we're going to try to mix uniforms on 0 to Li. So if you remember what we did, like the solution of our problem, it was either a uniform or a mix of a Dirac mass in 0 and a uniform distribution from 0 to something that depends on I. So the Li are going to be different across the i's. And in that case, if I have my xi's that are uniform between 0 and Li, my expectation is half of Li. And so I get that constraint that I have to satisfy. A little remark or observation, since all my xi's are positive, when I add them up, they will be larger than at least the largest one. And if I take, instead of taking the largest one, I just take the one that is uniform on the largest interval, then there is a probability that is strictly positive that this xi associated with the largest interval will be pretty close to Li. And so I know that there is a positive probability that this sum is going to be larger than the max of the Li's. And this is going to be a necessary condition for my things to be for my mixing to be possible. This little observation ensures that if I don't have this condition, then I cannot mix my variables. And it turns out that this is actually an if and only if conditions, not only for uniform measures, but for measures that have monotone decreasing density and are supported on 0 on the interval between 0 and Li. This has been proven by Wang and Wang in 2016 and by Zimi independently in like 2 years ago. Okay, and using that, if you remember, we have to mix random variables that are either uniform between 0 and something, and a mixture between Dirac mass and 0 and a uniform. And a mixture between Dirac mass and 0 and a uniform is more or less something that is a density that decreases very fast around 0. And using these results, we will be able to show that, yes, under some condition, we can mix our low-dose solution. And this translates into the following. So I have to be able to mix both my player A and B to ensure that my Blotto solution is a Blotto solution. And so each constraint that I transform my Blotto solution to Blotto solution for player A and for player B give me a condition for mixability. And those two conditions are different. One is saying that the Vmax has to be less than 1/2. So I'm in the symmetric case, sorry. I'm in the case where the value of the battlefield are the same for each player. So I have these two conditions. One is saying that the maximum value is less than 1/2, and the other one, the maximum value is less than gamma. And if you remember the value of gamma, it's the ratio of the two budgets. So I end up that I'm able to turn this Blotto solution into a Blotto solution if and only if I have this constraint that is satisfied. So there is a battlefield that is not worth more than half of the ratio of the two budgets. But we know that there are Nash equilibria, or at least one. So there will exist a Nash equilibrium in any case. So we expect that the solution will just be different from the Blotto game. So now the next question is, how do we compute this mixture? And we're going to see that, so we came up with an algorithm, and we're going to see that it looks like something that you might be familiar with if you are familiar with Wasserstein-Berry centers. So we can see the coupling problem as a multi-marginal problem. How do we do that? Well, the variance we are trying to minimize is among all the couplings that have the prescribed marginals. And so we can write our problem. Without loss of generality, we can assume here that the random variables are centered. And so the variance is exactly equal to the sum of the square of the sum. And therefore, our problem is minimize the coupling gamma such that the average value of the integral of this sum squared against gamma is minimal. And if people are aware of the Wasserstein-Berry centers, there is something in the Wasserstein-Berry centers that look a lot like this. So if I write it like this, so I just developed my square. All the products that are not cross products are independent of the coupling, because they're just xi squared. It does not depend on the coupling. So I end up just looking at the cross products. And this is exactly, when you change the sign, this is exactly the cost that you end up in the Wasserstein barycenter problem. So you have the opposite problem, where you're trying to maximize trying to maximize, to minimize the opposite of this thing. However, we know that this is usually a hard problem algorithmically, especially in the dimension. And here our dimension is basically n, what plays the role of the dimension. So it's going to be exponential in n. And we want to avoid that. And to avoid that, we're going to exploit the real structure of our problem. So we have a particular problem. We're not trying to mix anything, any distributions. We're trying to mix certain distributions. And the idea is that in our problem, because of its special form, we're going to be able to reduce our mixing of n marginals into the mixing of just 4 marginals. So how do we do that? The first step is the first step to the algorithm, is to do that. We use for that the Carter-Theodori theorem. So the Carter-Theodori theorem is saying that when I'm in Rn, if I have a set that has potentially infinitely many number, but just even a large finite number, the convex hull of this set can be written as the points, or like every point in the convex hull of this set is a barycenter of at most n points that belongs to the original set. Okay, so basically, n plus 1 point. So basically, if I have 3 points here, well, the convex hull is the whole triangle. But for every point that is inside, it's not the barycenter of 2 points that are in my original set. If I do that, I just get the edges of my triangle. If I want to have the point inside, then there's the barycenter of these 3 points, and then I can have all these points. But if I were to take 4 points, then my convex hull would be that. But for every point inside the convex hull that I have here, then I can write it as the barycenter of 3 points that are in my original set. So I don't need to go larger than 3, even though I can add more and more points. And Carter-Theodori theorem states that when I'm in Rn, I don't need more than n plus 1 points to mix, or to, sorry, not to mix, but like to describe every point as a barycenter of this point, every point in my convex hull. So we use that, and thanks to that, we're able to say that we can, instead of having to mix distributions that are sometimes uniforms and sometimes mixture of uniform and Dirac mass, we're going to end up having to couple only either just uniforms or just uniform except one that is possibly a Dirac mass in a mixture of a Dirac mass in 0 and a uniform. So we get rid of some complexity by doing that. And in the end, we end up with the problem of now I just have to mix a bunch of uniform and a mixture of a uniform and a Dirac mass. So the next step to get that reduction, is to actually propose a coupling for these things that will end up to be built on a coupling of just 4 random variables. So how do we do that? First, I will couple my 2 first random variables. So in here, I wrote my uniform distributions and the last one that I have to mix together. I order them in an increasing number of lengths of the uniform. So the first thing I do is I couple my first 2 uniforms by saying they are both U1, a uniform between the 1 and 1 here, multiplied by the length. And then I take the 2 others, for example, and then I say these 2 are like L3 times U2 and L4 times U2. And now I just have to couple U1, U2, and my last uniform and my last measure. And I will be able to couple everything else. So I suggest one coupling, 2 by 2 like this. That that makes me, that brings me into a problem that now I just have to mix U1, U2, and U3 and D. So it is not very clear that this is going to not blow up my problem and like make it not mixable anymore. But if you do it in a nice way, like there is a way to do it without losing the mixability. So by this little trick in some way, you can reduce your problem to n variables that I had to couple into just 4. And then the last problem is now I just have to mix my 4 random variables. So I don't have the issue that this is exponential in n. I don't have this issue anymore. So this n is 4, yeah, because n equals 4. So there are different ways to do that. So this is a linear problem. So I could use standard off-the-shelf things. But we want to do something a bit faster than that. We could also use synchron iterations. The problem with that is the synchron is going to give me something that is with a small variance, and I want to have something to be able to play that has variance 0. So I want an actual solution. What I want to lose maybe is my constraint on my marginals. Maybe my constraint on the marginals might not be perfectly satisfied, but I want my solution to be of variance 0, which is not what the algorithm do. So to do that, we will modify the synchron algorithm to obtain what we want. And how do we do that? We just realize that if I want to mix, I go back to just 3 random variables to be able to describe things more easily. Let's say I want to mix 3 random variables so that their sum is equal to 0. So the expectation has to be 0. This is the same as just actually mixing my first 2 variables and just calling minus z my last variable. And of course, I have this constraint on my last variable that has to be the minus the distribution that I had for z. So how do I do that? So this is my coupling matrix. So basically at the line 2 and the row 4, I have my probability of x equal 4 and y equal 2. And I will iterate synchron algorithm here, which is just saying alternatively on the row and on the column, I will scale so that the condition, like I will just multiply each row, each column, so that it's satisfied at the end my constraint on the marginal. And what I will do here is that if I see that when I sum up the values on the diagonal, this corresponds to the value of my sum. Like if I sum up the last value over there on the diagonal, so there is just 1, this is the probability of x plus y equal 10. And if I do that for each row, I have these probabilities for each value that I'm looking at. And by doing that, I can scale this time iteratively between the row, the column, and the diagonal. And by this, we maintain a coupling that does satisfy my budget constraint, and that will, with each iteration, get closer and closer to my marginal constraint. Instead of having, of reducing my goal every time, like my objective function every time, like what synchron does, this ensures that my optimal solution is attained, but then I'm getting closer and closer to have my marginal constraint satisfied. So we've been doing that, and then we've done some computation to be sure that whatever error, mistake we make, or like error we have from not going to the end of the algorithm propagates well when we go from Blotto to Blotto solutions, and like the different steps that we did where we like remove the constraint and we did some reduction from n random variables to 4. So if we do that backward, we have to be sure that the errors does not blow up. And then we did this like, instead of mixing all the random variables we had at the beginning, we just mixed uniforms and a mixture. So we do all that backward, and we make sure that things don't go bad, like the error does not explode. And we had this like approximation errors that I mentioned here. So basically we have in the metric, in the value symmetric case, we can have an epsilon optimal strategy with something of order epsilon to the 1 over epsilon to the 4th, and n squared, where n is the number of parallel fields. And we have this, in the general case, we have this m that we wrote here, that is a value, the maximum value of the ratio of the value of the parallel fields that appear in the bound. And yeah, to sum up, we have a new approach to compute approximation of Nash equilibrium in the Blotto coupling. And this is the first Nash equilibrium that is like the first such solution for the asymptotic values. But still, not everything is solved. And in particular, the issues that remain is that now the Blotto Nash equilibrium are not the same as the Blotto ones. And so it's going to need a new approach. And that's it.